Somewhere beyond the reach of every telescope we have ever pointed at the sky, beyond the last planet, beyond the edge of the sun's own magnetic bubble, a machine the size of a small car is still alive. It was built in the 1970s with computing power weaker than a digital watch. It runs on a nuclear battery that loses 4 watts every year. Its 3 onboard computers share just 68 kilobytes of memory between them, and its processors tick along at 250 kilohertz, roughly 1/1,000,000th the speed of the phone in your pocket. It is held together not by modern engineering miracles, but by the sheer stubbornness of a team that has refused to let it die. And right now, in 2026, nearly half a century after it left Earth, Voyager 1 is doing something no human-made object has ever done before, and what it is sending back is genuinely changing what we understand about the universe. In November 2026, Voyager 1 will reach a distance of exactly 1 light day from Earth. 1 light day is the distance that light, traveling at nearly 300,000 kilometers per second, covers in a full 24 hours. That works out to roughly 26 billion kilometers, or just over 16 billion miles. NASA has confirmed the milestone, and when it arrives, it will mark the first time in history that a human-made object has ever been that far from home. To send a command to Voyager at that moment and receive a confirmation back will take a full 48 hours. That number, more than almost any other in the history of space exploration, captures what Voyager 1 has actually achieved. It is not just far away. It is so far away that light itself takes a day to close the gap. The mission that made all of this possible began with a cosmic coincidence. Once every 176 years, the outer planets of our solar system arrange themselves in an alignment that allows a spacecraft to use each planet's gravity as a slingshot, picking up speed without burning a drop of extra fuel. That alignment was available in 1977, and NASA seized it. Voyager 1 launched on September 5th of that year, not built to last more than a few years, not designed to go anywhere near as far as it eventually went, and not expected to still be transmitting data in the 21st century. The planetary alignment that made it possible won't come around again until the year 2153. Nobody alive today will see it repeated. In its early years, Voyager 1 delivered some of the most astonishing photographs and scientific measurements in the history of space exploration. Passing Jupiter in 1979, it discovered that the planet's moon, Io, is a violently volcanic world, erupting constantly, nothing like the cold, dead rock scientists had assumed it would be. It found 2 moons nobody knew existed, Thebe and Metis, and detected a faint ring around the gas giant. At Saturn in 1980, it discovered 5 previously unknown moons, identified a new ring called the G ring, and turned its instruments on Titan, Saturn's largest moon. What it found there stunned researchers. A thick, hazy atmosphere made predominantly of nitrogen, the same gas that makes up most of Earth's own air. These were not minor findings. They were world-redefining discoveries made by a machine the size of a Honda Civic. After Saturn, Voyager 1 kept going. There were no more planetary targets on its trajectory, only open space in the direction of the constellation Ophiuchus. For decades, it traveled outward through the heliosheath, the turbulent outer region of the sun's influence, where the solar wind slows and churns before meeting the pressure of interstellar space. Scientists had theories about what lay beyond that region. They had models, predictions, and confident expectations about what Voyager would find when it finally crossed the heliopause, the outermost boundary of the sun's magnetic bubble. When Voyager 1 finally crossed that boundary on August 25th, 2012, becoming the first human-made object to enter interstellar space, some of those expectations held up. Others fell apart entirely. The biggest surprise at the heliopause crossing was the magnetic field. Every model scientists had built predicted that when Voyager crossed from the sun's magnetic domain into interstellar space, the direction of the magnetic field it measured would change sharply. The sun's magnetic field and the galaxy's magnetic field point in different directions, and crossing the heliopause was supposed to feel like stepping from one room into another with a sudden clear shift in the field orientation marking the threshold. It never happened. Voyager 1 crossed into interstellar space, and the magnetic field direction barely changed. Scientists debated for years whether the spacecraft had actually made the crossing at all, until a separate measurement settled the question. In April 2013, Voyager's plasma wave instrument detected oscillations in the ionized gas around it, revealing that the density of electrons had increased by roughly 80-fold. That density spike was unmistakable. Voyager was in interstellar space. The magnetic field just hadn't behaved the way anyone expected. That magnetic field anomaly is not a footnote. It is a genuine scientific mystery that forced researchers to rebuild their models of the heliopause from scratch. Merav Ofer, a space physicist at Boston University, described the broader lesson bluntly. "We know now how little we know about the heliosphere," she said. "It is way more complex, way more dynamic than we thought." David McComas of Princeton University put it another way, comparing the Voyager data to 2 tiny biopsy samples taken from a vast and unknown body. Two data points from two spacecraft cannot tell us the global three-dimensional shape of the outer heliosphere, he noted. We are mapping an ocean with two probes dropped into it at different spots. Everything we think we know about the shape and structure of the sun's protective bubble is, in a real sense, still an educated guess built on the thinnest possible observational foundation. Voyager didn't just raise new questions. It revealed how many old answers were incomplete. What Voyager 1 has been sending back from interstellar space since 2012 has continued to produce surprises. In December 2018, scientists announced that Voyager's plasma wave subsystem had detected something they described as a constant drone, a persistent low-frequency hum of vibrations propagating through the ionized gas of the interstellar medium. The interstellar medium was long assumed to be essentially quiet, a thin and featureless void between the stars. Voyager revealed that it has its own acoustic character, its own rhythm of plasma waves that travel through it continuously. Bill Kurth, a space physicist at the University of Iowa who has worked on Voyager instruments since 1974, described the discovery as part of a mission that had transformed from a planetary expedition into something closer to an expedition of humanity itself. But the mission is racing against physics. Voyager 1 is powered by a radioisotope thermoelectric generator that converts heat from decaying plutonium into electricity. Every year, that generator loses approximately 4 watts of output. After nearly 50 years of operation, the power budget is now so tight that every watt matters. Engineers have been managing a controlled shutdown of the spacecraft's systems for years, turning off heaters, sacrificing redundancy, and deciding which instruments are worth keeping alive at the cost of everything else. On February 27, 2026, during a routine roll maneuver designed to calibrate the magnetometer, Voyager 1 experienced an unexpected drop in power. The team realized that if the power fell any lower, an automatic failsafe system would activate, shutting down components in ways that could be difficult or impossible to reverse from 16 billion miles away. To prevent that from happening, NASA made a difficult decision. On April 17, 2026, engineers sent a command to shut down Voyager 1's low-energy charged particles experiment, known as the LECP. That instrument had been running almost continuously since the spacecraft. Launched in 1977, nearly 49 years earlier. It had measured cosmic rays, studied the structure of the solar wind, and helped scientists detect the changes in particle density that ultimately confirmed Voyager had crossed into interstellar space. Matt Hill, principal investigator for the instrument at Johns Hopkins Applied Physics Laboratory, acknowledged the weight of the moment. The LECP had let the team sense the changes in the region around the spacecraft that determined when it had crossed from the solar system into interstellar space, he wrote. He added that the team holds out hope that engineers might find a way to power it back on, but noted that their track record of performing miracles will eventually run out. The plan engineers are working toward to prevent that outcome is called the Big Bang, a nickname given to a power management technique that they hope will unlock enough additional electrical capacity to keep Voyager 1's remaining instruments running beyond current projections. The approach is being tested first on Voyager 2, which has slightly more available power and is closer to Earth, making it a lower-risk candidate for the experiment. Tests on Voyager 2 were scheduled for May and June 2026. If they succeed, the same technique will be applied to Voyager 1 no earlier than July 2026. If it works as hoped, there is even a real possibility that the LECP instrument could be turned back on, resuming the cosmic ray measurements it was collecting when it went dark in April. The team describes the stakes of the Big Bang simply. It is the spacecraft's best remaining chance at a significant extension of its scientific life. The stakes of getting any of this wrong are exceptionally high. Suzanne Dodd, Voyager project manager at NASA's Jet Propulsion Laboratory, described the spacecraft's current state in stark terms. Everything on board is single string. That phrase means what it sounds like. There are no backup systems left. Every component that remains operational is the last of its kind on the spacecraft. If it fails, there is no redundant system to take over. On top of that, between May 2025 and February 2026, Deep Space Station 43 in Canberra, Australia, the only antenna on Earth capable of sending commands to Voyager 1 was offline for major upgrades, with only limited communication windows available in August and December 2025. For the better part of a year, humanity's farthest spacecraft was effectively unreachable. The antenna is back online now, but the episode illustrated precisely how fragile the remaining thread connecting us to Voyager has become. There is something almost incomprehensible about the technology gap between Voyager 1 and the civilization now trying to keep it alive. Its computers communicate with Earth at a downlink speed of 160 bits per second. Your home internet connection is roughly 1,000,000 times faster. Commands sent from Earth travel to the spacecraft at 16 bits per second. The computers themselves run at 250 kilohertz and share 68 kilobytes of total memory, less than a single photograph taken on a modern smartphone. The engineers keeping this machine alive are not just operating a spacecraft. They are maintaining a relationship with a system so old and so resource-constrained that every decision made on Earth must account for the 24-hour round-trip delay that separates a command from its consequence. There is no real-time control. There is only careful planning, precise instruction, and then a very long wait. Voyager 1 carries with it the golden record, a 12-inch gold-plated copper disc designed to survive the conditions of interstellar space and communicate something of what humanity is to any civilization that might one day find it. The record contains greetings in 55 languages, 115 photographs of life on Earth, sounds ranging from wind and rain to music from a dozen cultures, and a map of our location in the galaxy encoded in pulsar timing data. Carl Sagan chaired the committee that selected its contents, describing the project as a message in a bottle cast into the cosmic ocean. That bottle is now more than 24 billion kilometers from the shore it was thrown from, and it is moving faster than anything else humanity has ever built, at roughly 61,000 kilometers per hour relative to the Sun. When Voyager 1 reaches the 1 light day milestone in November 2026, it will have traveled only 0.027% of the distance to the Sun's nearest stellar neighbor, Proxima Centauri. The Oort cloud, the vast reservoir of icy bodies that marks the true gravitational edge of our solar system, still lies roughly 300 years of travel ahead of it. It will take another 30,000 years after that for Voyager to fully clear the cloud and be genuinely outside the solar system in every measurable sense. And in the year 40,272, astronomers have calculated that Voyager 1 will pass within 7 light years of a faint red dwarf star called Gliese 445 in the constellation Camelopardalis. Nobody alive today, and no one born for hundreds of generations to come, will ever witness that moment. Despite all of this, despite the failing power and the shuttered instruments and the impossibly slow data rate, Voyager 1 is still doing science. As of 2026, 2 instruments remain operational, the plasma wave subsystem and the magnetometer. Those 2 tools are measuring things no other instrument anywhere can measure, because no other instrument is where Voyager is. Every reading the magnetometer takes in the interstellar medium is a data point from a region of space that has never been directly sampled by anything before. Every oscillation the plasma wave system records adds to a picture of what interstellar space actually feels like at a physical level. The questions Voyager is still answering, and the new ones it keeps generating, are not trivial. Scientists still do not know the true shape of the heliosphere, and Voyager's data remains the primary evidence in that ongoing debate. What Voyager 1 represents is not just a technological achievement, though it is certainly that. It is a demonstration of something rarer. The willingness of a civilization to invest in a project whose full returns will not arrive within a single human lifetime, or even within several. The engineers who built it in the 1970s could not have known it would still be transmitting in 2026. The scientists now scrambling to preserve its last 2 instruments will not live to see what Voyager eventually tells us about the deeper reaches of interstellar space. And yet the work continues, year after year. Instrument shutdown by instrument shutdown, miracle by miracle. A machine held together by careful hands and older than most of its caretakers is still out there, still moving, still listening, still whispering home across 16 billion miles of darkness. And we are still, after all of this time, listening back.